Okay, so here's our starter. And it says an object initially at rest experiences a time-varying acceleration given by acceleration equals 2 meters per second cubed times time, for time greater than or equal to 0. How far does the object travel in the first 3 seconds? And here are your options. And this is a typical multiple choice kind of questions for AP Physics on the mechanics test. So you need to be able to do it very quickly. So some of the starters I'm going to be giving you for the rest of this year are going to be multiple choice questions from the AP tests. And there are published tests out there. There are also, those Princeton books and things like that. That's where I get these problems from. But anyway, so let's work it out and see what happens. You say that, and by the way, if you were doing this on an AP test, you would not do it the way I'm going to do it here. The way I'm going to do it here is very complete because I want you to see the solution. What do you need to do on the AP test? On multiple choice? You need to just rip. You need to go fast. Okay? But anyway, so we're given A, the acceleration, is equal to, well, first I'm going to say this. Acceleration, by definition, is dv dt. And the derivative of velocity, and that's equal to 2 meters per second cubed times time. And then there's no at t equals 0, the acceleration is 0, which kind of wonder how does it get started. Anyway, but what we're going to do is take the we need to figure out what delta x is. I mean, that's what we're trying to find. Well, I'm going to take this and I'm going to rearrange it. So in order to get delta x, I need to get delta v. So I say dv is equal to 2 meters per second cubed times time times dt. Now, this is a cool thing about differential calculus and integral calculus is that you can treat this is a fraction. It is a fraction. dv dt is a fraction. A little tiny velocity divided by a little tiny time. Okay, so that allows you to rearrange the equation. Well, what happens if I sum up all the little tiny dv's? From the initial velocity to the final velocity. Well, whenever you sum them all up, you have delta v. So this is delta v, which is v final minus v initial is equal to, well, I got to integrate this side, and I'm going to go from 0 to time t. Let's just go to time t for right now. We'll plug in the 3 seconds later. And so now you use the power rule. You keep the 2 meters per second cubed, and then you multiply t times t is t squared. And then you have to remember using the power rule to divide by the new exponent, right? And then you're going to evaluate that from 0 to t. That is, you want this dt to be a delta t. But what's our t initial? 0. So when you plug it in, the whole thing is 0. So anyway, this becomes, now, what's true about v initial? It says it starts from rest, initially at rest. So that means this thing is 0. And so this gives me an equation for the final velocity, and I'll just leave it as v instead of v final, as a function of time is now, this cancels. You can put 1 meters per second cubed times t squared. And that's our function for velocity as a function of time. Okay? Dimensionally, does it make sense? Well, what do you need if velocity? What is velocity in units? It's in meters per second, right? Well, do you get meters per second here? Yes, you do. You have meters per second cubed here. We got a second squared up here. That cancels with the second cube. You have meters per second. Always check the units. Always check the units. If the units come out dimensionally correct, you've probably done it right. Why does E equals mc squared? Because the units work. Okay? Always check the units. Now, velocity. What is velocity? Well, velocity is dx dt. Okay, so now we can just do the same thing. We can say, so dx is equal to 1, and you don't need to keep the 1 meter per second cubed, but I'm going to just let the units, show how the units are canceling, times dt. Okay, and now what we want to do is we want to sum all the little dx's, and that'll give us delta x. Well, here we need to sum all the products of this times time, or little tiny chunks of time, from 0 to t. And now we use the magical power rule once again. So this is going to be t, well, you've got the 1 meter per second cubed times t to the third over 3, and it's a definite integral, so we're going to evaluate it from 0 to time t. So we plug the t in, we plug the 0 in, we can just, so we have our final expression for delta x is 1 meter per second cubed over 3 times t cubed. And dimensionally, does this make sense? This is in meters. Well, this is seconds cubed, cancels with the second cube right there. Yeah, it makes sense. But now we want to know how far we've gone after 3 seconds. So we plug in 3. So delta x is equal to 1 meter per second cubed over 3 times 3 seconds cubed. And that will give us, well, 3 times 3 is 27, divided by 3 is 9. So delta x equals 9 meters. So the answer would be A. So that is the correct answer. Now, it took me, I don't know how long this video, 7 minutes. It took me 7 minutes to explain all this. You need to do this in about 1 minute and 20 seconds on average on the AP test. Well, you get 45 minutes to do 35 problems. But I have to say, though, that if you know what you're doing, and hopefully by the time you take the AP test you know what you're doing, you can just rip right through this, right? I mean, this wouldn't take that long to do. So, anyway, that is how to do that. And there will be a problem similar to this on the exam, on my exam. That is all.